Okay, so today we're going to be looking at two means instead of proportions this time. So t-test and using our t-distribution to create our intervals here. So remember, our notation is a little bit different, and this has been an issue. Okay? Our notation for our parameter here is this mu symbol. It is a U with kind of an odd-looking thing on the front end here. Okay? This is not an M. It is not an M that I'm writing like in cursive or something. It is a U with an extra tail on the left-hand side. Okay, and remember for mean, our statistic is the X with the bar over the top. And again, we're talking about two samples here, so we're going to have sample size 1 and we're going to have sample 2 that we need to take into consideration. So let's first look at our sampling distributions. So what we have here are the sampling distributions of 10-year-old girls and 10-year-old boys. Okay, and so the first one here, this is our sampling distribution of females. This was created on software, and this is 1,000 repetitions. So there are 1,000 little dots here in our dot plot. Okay, and so our shape of this is approximately normal, because in the problem setup, which if you would like to read it, is on page 636. Okay, our population distribution is normal, so that means our sampling distribution is going to be normal. Our center here is centered around the mean, okay, and our mean here is about 56.4, the highest point there on our curve. And our spread here, okay, is calculated using our formula here, because this each sample, so remember this is a sampling distribution, so this is 1,000 different samples. Each sample is 12 girls. So when we do our 10% conditions, there are more than 120 10-year-old girls in the United States. So we can use that formula for spread. Okay. As for the second one here, this is our sampling distribution of males. Again, normal, because our population distribution is normal. Our mean this time is centered around 55.7. Okay, and then we can use our same standard deviation formula, because in the male samples, each one is a sample of 8 males. So there's a sample of 8 males. There's 1,000 samples of 8 males. Each dot here is one of those samples of 8 males. Okay, and so it's the average height. It's the mean height of each sample. And our third sampling distribution over here on the end is our sampling distribution of the difference between the two means. Okay, and so this one, I believe, is done females minus males. So we're looking to get more positive values just because it's a little bit easier to work with. Okay, and remember, when we're looking at the sampling distribution of the difference between the two means, okay, we're going to see that our mean is located there at the difference, at the average difference between each one of the samples. Okay, so each of these dots on the third one here, so each one of these little dots on this dot plot is a difference between the female sample and the male sample. And so our mean is centered around 0.67 inches. Our spread is at 5.6 inches, and our shape is approximately normal. And if we look at our conditions that go along with this of our sampling distribution here, right, we've got our shape being approximately normal if the sampling distributions are normal of the males and of the females. So when the population distributions are normal, my sampling distribution is normal. If not, I need to have my sample sizes greater than 30. I don't have sample sizes greater than 30 in this case. I have sample sizes of 12 and sample sizes of 8. However, my populations were normal. My mean is going to be my average difference between the two. And the mean of the sampling distributions there, okay, is going to be my difference. And then my standard deviation, okay, same as before, I'm adding here. Okay, so I take my standard deviation of the first sample, add it to the standard deviation of the second sample, okay, and then I'm going to square those. Okay, or I'm going to take the square root of those, and you'll notice this standard deviation is squared, This one is squared, divided by the sample. Let's make sure we separate those numbers out. Right, so this is my standard deviation squared of the sample, of sample 1. That's why I have that subscript of the 1, over the sample 1, plus the standard deviation squared of sample 2 over sample size 2. And then I take the square root of all of that. And remember, what that value means is that the difference in the sample mean will be about whatever our standard deviation value is from the true difference in means on average. So in this particular example here with the males and the females, the difference in our sample mean, so hold on, I don't remember what the number is. There we go. So the difference in the sample mean will be about 1.56 inches from the true difference in means on average. Okay, so let's go through the example that we have here. So take a second and read this example about the fast food restaurant. Okay, so for this question, we are asked in part A to describe the shape of the sampling distribution. Well, the shape of this particular sampling distribution is going to be normal, and I know that because my populations are both normal. So I have a normal distribution for the large cups. Sorry, it's not writing. So I have a normal distribution for the large cups, and I have a normal distribution for the medium cups. So my shape here is approximately normal because both population distributions are normal. Okay, part B of this question asked to find the mean. So we're asked to find the mean here, and the mean would be, the difference here is going to be equal to these. So we're going to have 27 was our mean for the large cups, 17 for the small. So our mean difference between the two is 10 ounces. So that's our mean difference. And then the last part, part C, asks for standard deviation and interpretation of standard deviation. So if we're doing standard deviation for this problem, okay, right, I'm going to use my sample 1 standard deviation, which is 0.8, and I'm going to square that over, I took 20 samples, and then I'm going to add that to my sample 2 standard deviation, and I took 25 samples of those, and I'm going to get 0.205 ounces. And my interpretation of that is then that the difference in the sample mean will be about 0.205 ounces from the true difference in the means on average. Okay, so let's look at constructing a confidence interval for the difference between two means. So when our conditions are met here, and our conditions are the same as before, they both need to be random, okay, or they need to come from two groups in a randomized experiment. Both samples need to meet our 10% conditions, and both samples need to meet our normal or large sample. And remember, if n is not greater than 30, then we have to look at the graph. And remember, you have to draw one of those graphs. You can't just say you looked at it. You have to sketch one of those graphs out. And it doesn't matter which one of them you sketch out, whether it's a box plot or it's the histogram. It doesn't matter. You just need to sketch one of them out. Remember, normal large sample is for means. Your large counts, your n times p and n times 1 minus p, that is for proportions. Okay? All right, so if we're constructing our two sample interval here, okay, our formula is going to be the same as it was, right? Our test statistic plus and minus our critical value, which this time is going to be t, times our standard deviation. And you'll notice our standard deviation here, we are using the standard error. We're using the standard deviation of the samples. We are not using the standard deviation of the whole population because it's very unlikely that you would know that. If you knew that, you would calculate a Z statistic, but it's going to be very, very rare that you would know that, and you will not see that on your AP test. Okay, so we will go ahead and use the standard error because it's going to be highly unlikely that we're going to actually know our standard deviation for both populations. Okay, so we'll be using the sample standard deviation. And we will be calculating our test statistic as a T, remember, because we are going to be using the sample standard deviation since we will be unlikely to know the population, which is going to be our statistic. Remember, this is our statistic minus our parameter over, and we'll put that standard error in there, the standard deviation of the first sample squared divided by the sample size plus the standard deviation of the second sample squared divided by that second sample size. And that's going to get us our test statistic, which tells us how far this difference here, how far the sample distance is from the mean in standard deviation units. This is what all of our test statistics mean. When we get the 1.96 or the 2 point whatever, it tells us that this is how far the sample is from the mean in standard deviation units. That's what a z-score meant a long time ago, and that's how we can use that test statistic to then find the probability under the normal curve. Okay, all right, so let's look at our example for this. Okay, so here's our example here about the Wade Tract Preserve in Georgia, comparing the northern and the southern ends of the forest. So take a minute and read your example and look at your data here. Okay, so the first question, part A here, has us just looking at the data and comparing the sizes of the longleaf pine trees in the two halves of the forest. So let's start here first with looking at the northern end. So looking at the graph here, on the northern end, so the top one here is our northern end graph. So on the northern end, the data looks kind of skewed to the right, where on the southern end, it looks skewed to the left. Okay, if we look at our mean and median here, so both the median, remember, here's our median on our graph, right? So our median, we're given the mean in the data here. So the median and the mean is in the south is greater than in the north. Okay, I have more variability in the north though. If I look at my standard deviation in the north is bigger than it is in the south. Okay, so I have more variability in the north. I've got a greater standard deviation. Okay, I have a larger range, a larger IQR on my box plots. Okay, so greater range, greater IQR. Okay, and so we've got more variability in the north, but the average size in the south is larger. Okay, we're skewed left in the south, skewed right in the north. So that would be our comparison there of our data. And now let's go looking at part B. It's asking us to construct and interpret a 90% confidence interval for the difference in the diameter at breast height. That's what the DBH stands for, diameter at breast height of longleaf pines in our northern and southern parts of the preserve. So let's go ahead and construct and interpret that interval. So because we're constructing and interpreting an interval, we're going to have to do our 4 steps. So our first step here is our state. I don't know why it moved that around instead of writing. Okay, so our state part here. So I'm doing a confidence interval. So we want to estimate, because I'm trying to figure out a range of values that would include the true value. So I'm trying to estimate the actual difference. So I'm trying to estimate the difference between the mean of, and we're going to do south because they're larger, so I get more positive values. South minus north, okay, at a 90% confidence level. Okay, and then I need to define both of those parameters, right? Where mu1 is the true mean diameter, we're going to do their abbreviation, diameter at breast height, okay, of all the trees in the southern half. All trees in southern half of forest. Okay, and mu2, because I have to define both of my parameters, is the same thing but in the north, right? It's my true mean at diameter at breast height, true mean diameter at breast height of all trees in the northern half of the forest. Okay, so that's my state part, defining both parameters, as well as stating my confidence level. So I stated my confidence level that I wanted it at. I defined both parameters, and I said what I'm trying to estimate here. Okay, part 2 is the planning stage. So in the planning stage here, I need to state what method of inference I'm going to use. So I'm planning here, so I'm going to use a 2 sample t interval if those conditions are met. And so I need to go through and I need to check all my conditions here. Okay, is it random? Yes, they were both in SRS. So both of our samples were a simple random sample of the population. Okay, I need to check my 10% conditions for both areas of the forest. Right, so I have a sample of 300 trees from each end, okay, or 30 trees from each end, which would give us 300. And so we can assume that there are more than 300 trees in both ends of the forest. And then because this is a mean, I need to do my normal large counts. And my graphs look a little skewed, but both samples are greater than or equal to 30, and 1 is 30 and 2 is 30, so I'm okay there on my normal large counts condition. So now let's move on to our do. And so in our do, we're going to be technology, just like we were in the proportion one. So let me pull up that picture for you real quick. Okay, so again, using your technology, you're going to use the 2 sample t interval test. So under stats, test, 2 sample t int, you're going to need to write that down that you use that. So you're going to, when you're doing your, quote unquote, doing your calculations, you're going to need to write down this name right here, the 2 samp t int. Okay, and then you're going to go ahead and you're going to need to input your stats. So you can put in your mean of the first sample. You'll need to put in the standard deviation of the first sample. You'll need your sample size. Okay, and then you do the same thing for the second, and then make sure you set your confidence level. Always click no for pooled. Okay, we do not want to pool the data like we did for proportions. Okay, and then when you calculate it, it's going to spit out your interval. It's going to spit out your degrees of freedom. Both of these you need to pull off of here. Okay, you need to write down your interval. You need to write down your degrees of freedom. And now we are on to the conclusion part. So we need to actually interpret what is happening here. So we are 90%, because this one asks for a 90% confidence interval, 90% confident that the true, that the interval, it was 3.9362 to 17.724. You can calculate this by hand or you can calculate it on the calculator. Like always, you know, you'll get slightly different values depending upon whether you calculate it by hand or calculate it on the calculator. These are the values that the calculator would have given us, since that's the way I think we're going to go with this. So we are 90% confident that the interval 3.9362 to 17.724 captures, so same interpretation as before, captures the true mean difference. Okay, and then again we're going to define that south minus north between diameter at breast height of trees in the south and north half of the forest. Okay, your subtraction order could be different. You could have taken the north and subtracted it from the south. Okay, since that's how the order was given to you in the data table there. Your subtraction order can be different. What that will do is it will make your intervals negative here. And what that would mean, so it doesn't really change, it doesn't change your number is still the same, but it would become negative because you'd have all those negative values there. And what that would mean is that would mean that the northern trees are smaller. By it being all positive now, that indicates that our southern ones are bigger than our northern ones. And if it was an all negative interval, it would indicate that our northern trees were smaller than the southern trees. Okay, so let's look at a significance test for the difference between two means. Okay, so if our conditions are met, so our conditions are the same as before, we're going to be testing our null hypothesis here of mu1 minus mu2 is our hypothesized value. Basically, mu1, remember, mu1 minus mu2 would equal 0. They'd have no difference, or they'd be the same, right? You can use either one of those null hypotheses, right? That these are my null hypotheses options. That mu1 minus mu2 equals 0, or that mu1 equals mu2. Okay, so here's our test statistic there. That's how we're going to find our t. We're going to find the p-value by putting that, of getting a t statistic that's that large or larger, based upon what our alternative hypothesis was, right? To the right is our alternative hypothesis is greater than. To the left, our alternative hypothesis is less than. Okay, and then both sides, remember, is our alternative hypothesis does not equal. And we're going to work a little bit more with interpreting p-value because we're still not quite getting that. Okay, and then we're going to have our degrees of freedom, which will be given to us when we go through our calculator work. Okay, so here's our example for our significance test here. So go ahead and take a second and familiarize yourself with the scenario. Okay, so let's perform our test to see if we have convincing evidence here. So it's our four-step process, like always, because we're performing our significance test. So our first part here would be our state, right? We want to perform a test of. And so our null hypothesis, we have our two options, right? Our null hypothesis can be mu1 minus mu2 is equal to 0, okay? Or it could be mu1 equals mu2. You do not have to do both of them. This is an either-or situation, okay? If you chose to do the subtraction one, then your alternative hypothesis would be that mu1, mu1 minus mu2 is greater than 0. And if I chose to write that the two were equivalent, then I would have that mu1 is greater than mu2. So I choose one or the other. What I don't want to do is I don't want to mix these. Okay, I'm not looking to mix. That's not okay. Okay, you have to go straight down the line. Okay, and then we have to go ahead and we need to define all of this. Right, so these are my hypotheses where mu1 is the true mean decrease equals the true mean decrease in systolic blood pressure. And this is a lot of context because this is an experiment, so you can only apply to this particular group of people. So the true mean decrease in systolic blood pressure for, because these were considered healthy, and it was black males, so we cannot apply it to any other race or gender, okay, like the ones in the study. Who take a calcium supplement. So so I've got mu1 is my true mean decrease in systolic blood pressure for healthy black men, like the ones in the study who take a calcium supplement. And then you also need to define mu2, right? So mu2 would be my true mean decrease in systolic blood pressure for healthy black men like the ones in the study who take a placebo. So it's going to be exactly the same. My definition for mu2 is the same as mu1. I've just changed what they're taking. They're taking a placebo as opposed to the calcium supplement. So mu2 is equal to the true mean decrease in systolic blood pressure for healthy black men like the ones in the study who take a placebo. Okay, and I need to define my alpha. Alpha equals 0.05 because they didn't give us one. So we're going to stick with our 0.05. Okay, so now we're going to shift over to our planning stage. All right, our step 2, which are planning stage. So I need to say what I'm going to do. So I'm going to do a 2 sample t-test if the conditions are met. And so then I need to run through my conditions, right? Random. Okay, so is random met? They were randomly assigned, the 21 subjects. So I've got my subjects for 21 healthy black men who volunteered to take part. They were randomly assigned, and that counts as random. Okay, so randomly assigned. Okay, I do not have to check my 10% condition because there was no sampling. These were people that volunteered for the experiment and there was no sampling. So I don't need to check my 10%. Okay, and I need to check but I do need to check my normal large sample because I'm doing the difference of the mean here. So my sample size here is 21. So, well, that's my whole population. So my sample size here is going to be 10 and 11, right? So N1 is 10, N2 is 11. Both of those are less than 30, so I need to check my graphs. So when I put that information in my calculator, so what you guys would do if you were solving this problem is you would put all of the data from the calcium into one list, all of the data for the placebo into the other list, and you would go ahead and you would just draw both of those graphs. Okay, your graphs should look similar to this. So when we're looking at these graphs, we don't have any strong skew, no outliers, so we're okay to go ahead and use our normal calculations, our normal approximations. Okay, and you remember if you turn both plots on, you can go ahead and you can graph both of them on the same graph on your calculator. If you don't remember how to do that, I can show you in class again. Okay, so on to the do part. So in the do part, we're doing a significance test. So I need my test statistic, which is going to be t equals 5 minus negative 0.273. Okay, so if you look at your sample information, if you went through and you put all of this into one list and this into another list, you can do your 1-bar stats, and it'll give you your mean for each one, and it will give you your standard deviation for each sample, right? And this is going to be minus 0 because mu1 minus mu2 should equal to 0, right? For our null hypothesis, that's what we are looking at here. And then I'm going to use my I'm going to square my standard deviation from the first sample, so 8.743 squared over my sample size of 10 plus 5.90 squared over my sample size of 11. So this will give me a test statistic of 1.604, and then everything else can happen through the calculator. Okay, and actually I think the calculator might even give you that test statistic. Let me pull that back up. So on your calculator here, again, you're going to stats and you're going to test just like you did before. And this time you're using a 2-sample t-test. Okay? If you went ahead and put this data in your calculator like you should have, you can go ahead and just pull it from list 1 and list 2. Our alternative hypothesis was that it was greater, mu1 was greater. Again, remember we do not pull our data, and you can go ahead and calculate it, and yes, this will give you your t-statistic. So you do not need to calculate your t-statistic by hand. You don't have to calculate that test statistic by hand, but you need to pull that data out. Remember, I need to pull out my t, I need to pull out my p-value, I need to pull out the t, I need to pull out the p, I need to pull out the degrees of freedom. Okay, I need to write all those things down. I need to write down what test I used, that I used the 2-sample t-test. I need to write my t equals 1.6, my p-value equals 0.064, and my degrees of freedom equal 15.59. I need to write all of those down so that I can get full credit here. You can also draw it, and it will show you what this looks like, what you were finding. I was finding the area of this end of the tail there. And once you've gone ahead and put all of that into your calculator, you need to go ahead and interpret. We need to go ahead and draw out our conclusion for this, which is going to be that, okay, so same as before, because the p-value, whatever that is, so because the p-value of 0.0644 is greater than alpha equals 0.05, we fail to reject the null hypothesis. The experiment, so this one was our experiment, so our experiment does not provide convincing evidence. So it does not provide convincing evidence that, and then lots of context here, right? That the true mean decrease, because that's what we actually looked at, so that the true mean decrease in systolic blood pressure for men that were in the study. So you could write all of that out again for healthy black males like the ones in the study, okay, or the true mean decrease in systolic blood pressure of males in the study that who take calcium than for men who take a placebo. So there's not enough convincing evidence the true mean decrease in systolic blood pressure is higher, because that was our alternative hypothesis, right? Our alternative hypothesis was going to be that calcium was better than a placebo. It was going to get a lower decrease in blood pressure, okay? A bigger decrease in blood pressure. Their blood pressure would have gone even lower. So it's that their true mean decrease in systolic blood pressure is higher for those who take calcium versus those who get a placebo. And I'm running out of room. So make sure you guys add all your context in there. Okay? And then part B for this has us interpreting that p-value. So when we're interpreting that p-value, okay, we've got to start with the fact that our null hypothesis is true, right? So assuming that that null hypothesis, whichever way you prefer to write it, okay, but basically that difference is true. Okay, when there is, and then we put in our p-value, a 0.0644 probability of getting, and what were we looking for? We were looking for a difference in mean. So of getting a difference in mean blood pressure reduction for the two groups, and we did calcium minus the placebo. Okay, calcium minus the placebo of 5.273 or greater. Okay, and that 5.273 is our mean difference between the two, because group 1 had a mean of 5 and group 2 has a mean of negative 0.273. Okay, so our mean difference between the two, 5 minus negative 2.73 gives us 5.273, or greater, because our alternative hypothesis was greater, by chance involved in the random assignment. By chance due to the random assignment of the groups. Because, you could have just had somebody that responded better than somebody else. Okay. So this is our interpretation of our p-value. If you look at your blue chart paper, that will tell you this, right? Assuming our null hypothesis, so we need to put that in there, is true, there is a p-value, 0.0644, of getting a sample mean and putting in that actual sample number, okay, by chance. Okay, so let's look at this last example here and see if you can tell the difference as to whether you should use paired T procedures or two sample T procedures. So let's look at the first one. To test the wear characteristics of two tire brands, A and B, one brand A tire is mounted on one side of each car in the rear, while a brand B tire is mounted on the other side. Which side gets which brand is determined by flipping a coin. Okay. So for this one, for A here, we would be using paired T procedures. I don't know why it does that. Okay, I'd be using paired T procedures here. This is a matched pairs experiment. The two treatments are being randomly assigned, okay, to each side of the same car. So this is a matched pairs experiment. For B here, can listening to music while working increase productivity? 20 factory workers agree to take part in the study to investigate the question. Researchers randomly assign 10 workers to do a repetitive task while listening to music, and the other 10 workers do the task in silent. This is a two sample T procedures. Okay, because I've got two distinct groups of workers. I've got one workers that are listening to silent, and one worker that are listening to music, and one worker that is in one group of workers that are in silence. That would have been a matched pairs experiment if they had had 20 workers do the task with music, and then the same 20 workers do it without music. But since they split it into two groups, that one gets music and one doesn't, this is two samples. And we'll work, these are the kinds of things that I want to be working with in class. Which method do I want to use? Because I think once y'all have the right method, you usually can go through it pretty well.